So in the last video, we went through the first three concepts for electromagnetism out of five. And I just want to show you a couple of simulations to visualize some of these things. So going back to concept one, an electric current produces a magnetic field. I want to kind of visually show you what we mean by a magnetic field. So this is the bar magnet, okay, a regular bar magnet. And this is a compass here on the left. A compass is also a magnet. It's just really small and really light. And it's suspended right in the middle with a pivot point so that the needle can rotate freely. So if I were to move the compass, let's say right here, you see it's reacting in response to the bar magnet. So here's the north pole of the bar magnet. And what's going on with the compass is that the north pole of the compass is repelling from the north pole of the bar magnet. And at the same time, the south pole of the compass is attracting to the north pole of the bar magnet. Okay, I can move the compass to some other spot. Let's move it right here. If I move it right here, what's happening? So the compass is now pointing sideways. So this north pole of the compass, it's getting attracted towards the south pole here. But it's not pointing directly at the south pole because at the same time it needs to be repelling away from the north pole of the bar magnet. Okay, so those two forces combined cause the compass to point sideways. So moving the compass anywhere, it'll point in a different direction depending on where I move the compass. So what's drawn in the background are basically a whole bunch of mini compasses. Okay, look carefully in the background and you can see it's not just like wallpaper to look pretty. It's actually showing something. It's showing which way a compass would point if it were placed in that position. So for example, I'll focus on this dot right here. So if I were to drag my compass right to this part, it's saying that the red part should point slightly downwards and slightly to the right, and the white part should point mostly upwards and slightly to the left. So I'll move my compass there, and that's exactly what it does. Okay, so in the background, these little mini compasses, all of them put together, we call that the magnetic field. So we say that this bar magnet is creating this magnetic field around it so that any compass placed inside the magnetic field is going to respond to it. Okay, so bar magnets do that. And what concept number one of electromagnetism is saying is that not only do bar magnets produce magnetic fields, but electric currents produce magnetic fields as well. Okay, the field may look different, but an electric current can also produce this field. So here's the simulation for an electromagnet. So an electromagnet or a solenoid is when you take a wire and you wrap it around into a coil. And what wrapping it around into a coil does is it concentrates a magnetic field inside the middle of the coil. Okay, but there's no bar magnet here. Okay, there's no bar magnet here, yet this whole magnetic field has been created. And this is being created by electricity. Okay, so all concept one is saying is that electricity can create a magnetic field. So if I move this compass, okay, this compass responds to the magnetic field created by this electricity. Now, if I turn the electricity off, bring it to 0 volts, now as I move my compass around, nothing happens. Okay, it's pointing in the same direction the whole time. Okay, that's because I've turned the magnet off. So there's a great advantage of having an electromagnet as opposed to a permanent magnet. Electromagnets can be turned on and off. I'll turn it on again. So now my compass responds to the magnetic field created. One more thing I'll show with this one is I can reverse the current. So I can basically flip the current from 10 volts to negative 10 volts, or flip the battery to the other direction. Okay, that's flipping. Look at the battery, it changes direction. And when I change the direction of the current, I change the direction of the magnetic field. Okay, look at the compass. It flips direction. All right, and then, so that was like concept 1 and 2. Okay, concept 2 was about solenoids and electromagnets. And concept 3 is that magnetic field applies a force on a moving charge. So I don't actually have a simulation for that one, unfortunately. But now I'll move on to concept 4, which says changing magnetic flux through a loop of wire causes electric current through the wire. Okay, so there's a new word here, flux, magnetic flux. So flux refers to how much magnetic field is going through a loop of wire. So in this simulation here, right here, okay, I've got just a couple of loops of wire here. Okay, it's not attached to any battery. Okay, there's no battery that's going to power this light bulb. And right now, nothing's really happening. So the word magnetic flux means how much magnetic field is going through the hole, through the loop of wire here. So as you can see, with this bar magnet here, it creates a magnetic field. It's strongest close to the poles, and you'll see that these little mini compass symbols, they are brighter. Okay, they drew them brighter near the poles to indicate that the field is pretty strong there. And it's weaker as you go further out. Look how faint these drawings are in the far corner here. So the magnetic field is pretty weak the farther you are from the magnet. So if you look inside the loop, there's a little bit of magnetic field right now going in through the loop. Okay, it's pretty faint still, so it's kind of weak, the amount of magnetic field going through the loops. So we call that the magnetic flux. That's how much magnetic field is going through the loops. Now, concept number 4 says if I change, and the key word is change. If I change how much magnetic flux goes through the loop of wire, then it's going to cause an electric current through the wire. So if I change how much flux is going through this loop, I'm going to create an electric current. So these blue dots are the charges in the wire. Right now there's no current, they're not moving. So by changing how much magnetic field goes through the loop, I can actually cause these electric charges to move through the wire. So how can I change how much magnetic flux goes through the loop? Well, I can move the magnet. Okay, as the magnetic flux is pretty weak right now, and the magnetic field is stronger closer to the magnet. So if I drag this magnet towards the right, I can create more flux through the loop. That'll change the flux through the loop. And according to concept 4, that should cause a current. That should cause these dots to move. And when these dots move, when there's a current, the light bulb should shine. So all of that, you have to watch for all of that happening as I drag this magnet towards the right here. And I can drag it back actually, and the same thing happens. So as the magnet is moving through, look at the blue dots, look at the current. You get a current as the magnet moves through, and the light bulb turns on. But it stops. Once the magnet stops, the current stops, and the light bulb stops shining. What if I stop right in the middle? See, with the magnet right in the middle, nothing's happening because the magnet is at rest. Okay, the light bulb only turns on when the flux is changing. So that's while the magnet is going through it. All right, so that's called the principle of electromagnetic induction. That's using magnets to induce a current Induce means to like make something happen. So using magnets to induce an electric current. That's why it's called electromagnetic induction. The faster I move it, the brighter the light is. Okay, well, it's not working out too well. There's a button here that says flip polarity. Flip polarity means this magnet's going to completely reverse, 180-degree flip. And that's actually going to cause a significant change of flux. It's basically going to reverse the flux completely. It changes direction completely. So that's going to be a big change of flux. And that should cause the light bulb to go really bright. And it goes really bright. But it only happens while it's flipping. Once it stops flipping, the light stops. So you may wonder, okay, how is this practical? Like, we want our light bulbs to be on the whole time. Okay, it's not really helpful to have a light bulb that turns on for just a split second and then it turns off again. Okay, we don't want to have somebody to have to keep pushing this flip polarity button in order to keep the light bulb shining. So that's where the role of engineers comes into play. How can we use this concept of electromagnetic induction and design something, okay, to design some kind of a setup where the light bulb can actually stay on without having to continually push some buttons. Okay, so that's what I'm going to show you here. Okay, so this is a simplified version, simplified conceptual lesson on how a hydroelectric electricity or a hydroelectric power plant works. That's using water, so hydro, using water to produce electricity. So we have our loops of wire attached to the light bulb that we want to be continuously turned on. And we know that we can use a magnet to make the light bulb glow. So what happens if we attach the magnet to a wheel and then we get something such as falling water to spin the wheel continually? Well, then the magnet will spin continually and that'll change the flux continually through the loop. Okay, so let's turn the water on. So as you turn the water on, the magnet continually rotates or flips over and over and over again. And that's causing a continual current through this wire. Now this current is going back and forth. Okay, look at the blue dots. They're going back and forth. That's because the magnet goes north to south half the time and south to north the other half of the time. So the current flips direction as it does that. But that's keeping the light bulb on a lot better. Okay, it's still not perfect. It's still kind of flickering a little bit. Okay, but it's way better. Now I don't have to push any buttons. Okay, my hands are off. I just let this run by itself. Okay, so that's already a huge improvement of trying to get constant light out of my light bulb. Okay, so this device is called a generator, an electric generator. Okay, so anytime you build something that uses mechanical energy, okay, anything that uses mechanical energy, so that's kinetic or gravitational energy, which would be the falling water and the spinning wheel. It's gravitational and kinetic energy. You turn that energy into electricity. We say that we are generating electricity. So that kind of machine is called an electric generator. This kind of setup produces an alternating current, as I discussed. And that's the kind of current that we get in our homes out of our electrical sockets. Okay, that's the kind of current that's produced by a hydroelectric power plant. It's also the kind of current produced by a nuclear power plant. So in a hydro plant, we use water that's falling. In a nuclear plant, we use a nuclear fission reaction, which produces a lot of heat. We use that heat to change water into steam, and we blast that steam into the wheel, or another name for the wheel is the turbine.